Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. The Earth's magnetosphere, our invisible shield. The Earth, a dynamic planet teeming with life, owes much of its habitability to a protective force field known as the magnetosphere. This magnetic shield, generated deep within the Earth's core, extends far into space, safeguarding our planet from the harsh solar wind and cosmic radiation. Understanding the magnetosphere involves delving into the Earth's magnetic field, how it interacts with solar wind, and the crucial role it plays in maintaining our environment. Formation of Earth's magnetic field. At the heart of the Earth lies a solid inner core composed primarily of iron and nickel, surrounded by a fluid outer core made of molten iron and nickel. The movement of this molten metal, driven by convection currents and the rotation of the Earth, generates electric currents. These currents, in turn, produce a magnetic field through a process known as the geodynamo. The Earth's magnetic field is not a simple bar magnet with a north and south pole. Instead, it is complex and dynamic, constantly changing over time. The magnetic poles wander, sometimes even reversing completely in a phenomenon known as geomagnetic reversal. Despite these changes, the magnetic field has persisted for billions of years, continuously generated by the dynamo action in the outer core. Structure of the magnetosphere. The Earth's magnetosphere is a vast, teardrop-shaped region surrounding the planet, extending tens of thousands of kilometers into space. It is shaped by the interplay between the Earth's magnetic field and the solar wind, a stream of charged particles emitted by the Sun. The boundary where the solar wind pressure balances with the Earth's magnetic field pressure is called the magnetopause. The distance to the magnetopause varies, typically ranging from about 60,000 to 100,000 kilometers on the day side of the Earth. On the night side, the magnetosphere is stretched into a long tail known as the magnetotail, extending several 100,000 kilometers. Inside the magnetosphere, several distinct regions exist, each playing a unique role. The bow shock. This is the region where the solar wind first encounters the Earth's magnetosphere, slowing down abruptly and forming a shock wave similar to the bow wave created by a ship moving through water. The magnetosheath. Located between the bow shock and the magnetopause, the magnetosheath contains turbulent and heated solar wind particles. The plasmasphere. This donut-shaped region, filled with low-energy plasma, co-rotates with the Earth and extends up to several Earth radii from the planet's surface, the Van Allen radiation belts. Discovered in 1958, these belts consist of two layers of high-energy charged particles trapped by the Earth's magnetic field. The inner belt is mainly composed of protons, while the outer belt contains electrons. The magnetotail. Stretching far beyond the Earth's night side, the magnetotail contains plasma flows and magnetic fields that play a crucial role in space weather phenomena such as auroras. Interaction with solar wind. The solar wind, a continuous flow of charged particles from the Sun, significantly influences the Earth's magnetosphere. When the solar wind encounters the magnetosphere, it transfers energy, momentum, and particles into it. This interaction is complex and depends on several factors, including the solar wind's speed, density, and magnetic field orientation. One of the most significant effects of the solar wind on the magnetosphere is the process of magnetic reconnection. This occurs when the magnetic field lines from the solar wind and the Earth's magnetosphere connect and realign, releasing a tremendous amount of energy. Magnetic reconnection is a key driver of space weather events, such as geomagnetic storms and auroras. Auroras. The northern and southern lights. Auroras, also known as the northern and southern lights, are among the most beautiful and visible manifestations of the Earth's magnetosphere. They occur when charged particles from the solar wind are accelerated along the Earth's magnetic field lines and collide with atoms and molecules in the upper atmosphere, causing them to emit light. Auroras typically occur in oval-shaped regions around the magnetic poles, known as auroral ovals. The color of the auroras depends on the type of gas and the altitude at which the collisions occur. Oxygen atoms at high altitudes produce red auroras, while oxygen at lower altitudes produces green. Nitrogen can produce blue or purplish-red auroras. Space weather and its impact. Space weather refers to the conditions in space influenced by the Sun and the solar wind that can affect the Earth's magnetosphere. Geomagnetic storms, caused by enhanced solar wind conditions such as coronal mass ejections, CMEs, or high-speed solar wind streams, can have significant impacts on our technology and infrastructure. During a geomagnetic storm, the increased energy input into the magnetosphere can cause the Van Allen radiation belts to swell, leading to increased radiation levels that can damage satellites and spacecraft. The induced electric currents can disrupt power grids, leading to widespread blackouts. Communication and navigation systems, particularly those relying on GPS, can also be affected. Protection provided by the magnetosphere. The Earth's magnetosphere acts as a protective shield, deflecting most of the harmful solar wind particles and cosmic rays. Without it, the atmosphere would be stripped away over time, much like what is believed to have happened to Mars, which has only a weak magnetic field. The magnetosphere also helps protect living organisms from the harmful effects of high-energy cosmic radiation. The magnetosphere's protective role is vital for human space exploration. Astronauts in low Earth orbit, such as those aboard the International Space Station, ISS, benefit from the shield provided by the magnetosphere, although they still receive higher radiation doses than on the Earth's surface. Future missions to the Moon or Mars will require careful planning and protective measures to deal with the increased radiation exposure outside the magnetosphere. Measuring and studying the magnetosphere. Understanding the magnetosphere and its dynamics is crucial for predicting space weather and protecting our technological infrastructure. Scientists use a variety of tools and methods to study the magnetosphere, including ground-based observatories, satellites, and computer simulations. Satellites such as the Cluster mission, the Van Allen probes, and the Magnetospheric Multiscale (MMS) mission have provided invaluable data on the structure and behavior of the magnetosphere. These missions use a combination of instruments to measure magnetic fields, electric fields, and particle populations, helping to unravel the complex processes occurring in the magnetosphere. Ground-based observatories, such as magnetometers and auroral cameras, provide additional data, allowing scientists to monitor geomagnetic activity and auroral displays. Computer simulations and models help scientists understand the interactions between the solar wind and the magnetosphere, predict space weather events, and assess their potential impacts. Historical context and discoveries. The study of the Earth's magnetosphere has a rich history, with significant discoveries spanning several centuries. The concept of the Earth's magnetic field dates back to ancient times, with early navigators using compasses to find their way. However, it wasn't until the advent of space exploration that the true extent and complexity of the magnetosphere were revealed. In 1958, the launch of the first artificial satellite, Sputnik 1, marked the beginning of the space age. Shortly afterward, the Explorer 1 mission led to the discovery of the Van Allen radiation belts, revealing the existence of high-energy particles trapped by the Earth's magnetic field. This discovery laid the foundation for modern space weather research and highlighted the importance of understanding the magnetosphere. Subsequent missions, such as the International Geophysical Year and the launch of numerous satellites, have expanded our knowledge of the magnetosphere. The Cluster mission, launched in 2000, provided a detailed 3D view of the magnetosphere's structure and dynamics. The Magnetospheric Multiscale (MMS) mission, launched in 2015, has provided unprecedented insights into the process of magnetic reconnection. Future directions in magnetospheric research. The study of the magnetosphere is an ever-evolving field, with new missions and technologies continually advancing our understanding. Future research aims to address several key questions, such as the mechanisms behind magnetic reconnection, the impact of space weather on human activities, and the behavior of the magnetosphere under different solar conditions. Missions, such as the European Space Agency's ESA, Solar Orbiter and NASA's Parker Solar Probe, are studying the Sun's influence on the magnetosphere and improve our ability to predict space weather events. Advances in computer modeling and simulation will also play a crucial role in enhancing our understanding of the complex interactions within the magnetosphere. One exciting area of research is the study of exoplanet magnetospheres. By understanding how magnetic fields work on other planets, scientists hope to gain insights into the habitability of exoplanets and the potential for life beyond our solar system. The human impact and awareness. Raising awareness about the magnetosphere and its importance is crucial for fostering a deeper appreciation of our planet's natural defenses. Educational programs and public outreach efforts can help people understand how the magnetosphere protects us from space weather and the potential risks associated with geomagnetic storms. Efforts to mitigate the impacts of space weather on our technology and infrastructure are ongoing. Governments, space agencies, and private companies are working together to develop strategies for protecting satellites, power grids, and communication systems from the effects of geomagnetic storms. Improved space weather forecasting and early warning systems are essential for minimizing disruptions and ensuring the resilience of our technological society. The Earth's magnetosphere is a remarkable and complex system that plays a vital role in protecting our planet and sustaining life. From its formation deep within the Earth's core to its interactions with the solar wind and its impact on space weather, the magnetosphere is a dynamic shield that safeguards us from the harsh realities of space. Through continued research and exploration, we are uncovering the intricate details of how the magnetosphere functions and its critical role in maintaining the habitability of our planet. As we look to the future, our understanding of the magnetosphere will not only deepen our appreciation of Earth's natural defenses but also enhance our ability to protect our technology and infrastructure from space weather impacts. The magnetosphere and climate. An intriguing area of research is the potential connection between the magnetosphere and Earth's climate. While the magnetosphere primarily protects us from solar and cosmic radiation, some scientists believe that changes in the magnetosphere may influence atmospheric conditions and climate patterns. For instance, variations in geomagnetic activity have been linked to changes in cloud formation, which can impact weather and climate. Understanding these connections is complex and requires interdisciplinary research, combining knowledge from space physics, atmospheric science, and climate studies. While the exact mechanisms remain uncertain, continued investigation into the interplay between the magnetosphere and climate will provide valuable insights into the broader impacts of space weather on our planet. The magnetosphere and human health. The magnetosphere also plays a role in protecting human health, particularly for astronauts and aircrew on high-altitude flights. Cosmic rays and solar energetic particles pose significant radiation hazards, which are mitigated by the magnetosphere. During periods of intense solar activity, such as solar flares or coronal mass ejections, the radiation levels can increase, posing greater risks to humans in space and at high altitudes. For astronauts aboard the International Space Station, ISS, or future missions to the Moon and Mars, radiation protection is a critical concern. Understanding the dynamics of the magnetosphere and space weather can help develop strategies to shield astronauts from harmful radiation. Enhanced monitoring and forecasting of space weather events are essential for ensuring the safety of crewed space missions. The magnetosphere's influence on technology. The magnetosphere's interaction with space weather has direct implications for our technology-dependent society. Satellites, communication systems, navigation networks, and power grids are all vulnerable to the effects of geomagnetic storms. For example, the March 1989 geomagnetic storm caused a major power outage in Quebec, Canada, highlighting the potential for widespread disruption. To mitigate these risks, scientists and engineers are developing technologies and strategies to protect critical infrastructure. This includes hardening satellites against radiation, implementing better shielding for power grid components, and developing early warning systems for space weather events. Collaboration between governments, space agencies, and industry is crucial for building resilience against the impacts of space weather. Conclusion: the invisible shield. The Earth's magnetosphere is an extraordinary and complex system that plays a fundamental role in protecting our planet and sustaining life. From its formation deep within the Earth's core to its interactions with the solar wind and its impact on space weather, the magnetosphere is a dynamic shield that safeguards us from the harsh realities of space. As we continue to explore and understand this invisible shield, we uncover not only the intricacies of its behavior but also its profound significance for life on Earth. The magnetosphere's ability to protect our atmosphere, shield us from harmful radiation, and influence space weather underscores its critical importance. Through continued research, technological advancements, and public awareness, we can better appreciate the magnetosphere's vital role and enhance our ability to protect our planet and its inhabitants. The study of the magnetosphere is not just a scientific endeavor. It is a journey into understanding the very forces that make life on Earth possible. As we gaze up at the night sky, marveling at the auroras or tracking the paths of satellites, we are reminded of the invisible shield that quietly and steadfastly guards our world. The Earth's magnetosphere is a testament to the dynamic and interconnected nature of our planet, a reminder of the delicate balance that sustains life in the vast expanse of the cosmos.